Okay, let me move closer to the microphone. Thank you very much, Ronnie, for this introduction. Thank you also to the organizers, in particular Alex and Guy, for organizing this wonderful event here today and for having me. It's a great pleasure to be back here. This is on visual SLAM, and in particular real-time capable direct methods for visual SLAM with applications to autonomous systems. I'm not sure the audience, I guess, is from all sorts of domains. The area that I work in, and I guess most of you, is this area of computer vision. And it's a growing area. It's attracted more and more interest over the last years, and you can see that in the numbers. To give you one example, last year I organized one of the biggest conferences in this field, the European Conference on Computer Vision. And whereas the previous conference had 1,500 people, so we booked a location that seats 2,200, figuring that should be more than enough. Turned out it was not enough. In the end, we had 3,300 delegates coming to Munich last fall. And there was another 1,500 on the waiting list that we could not account for. So that kind of shows you an impressive growth in the community, and we see that not just from one year to another, but consistently over the years, that the participation numbers in conferences double from a year to another, or even, in our case, triple. So this is quite a dramatic growth in the community. Why is that so? Well, one of the things that we see is that a lot of the technologies that we as a community have been developing are now actually starting to bear fruit, starting to actually work in the real world. And some of the applications, this conference is focused on one of the key application areas of computer vision, autonomous systems. We have worked in this field of autonomous systems since about, I would say, since I started as a professor in Bonn in 2005. We started working with Daimler. Here you see some examples of these collaborations. We put the camera in the car. At the time, things were not as, optimistic as they are today. Now everyone believes that the self-driving car will hit the market next year. Back then, this was not considered reasonable. So, for example, when I tried to encourage people at Daimler to put a second camera into their car, they said, no, it's not possible, it's too expensive. That is quite puzzling if you think that the car costs, $50,000, and the camera, if you mass produce it, maybe $2 or $3, and how, a $2, $3 camera can be too expensive for a $50,000 car was a mystery to me. But what it shows you is multiple things. First of all, it shows you one important thing: in the business, in the market, cost is a huge issue. And even if in the public they always talk about safety of self-driving car, cost plays a major role in whether things get deployed or not. But the other thing is that clearly in 2005, even the managers at Daimler did not believe in the self-driving car to ever show up. What changed the picture was not so much that I insisted on having a second camera, but at some point Toyota came out with a second camera, and then we needed a second camera literally the day after. And so with two cameras, we started developing scene flow algorithms. Here's one example of something we did back in 2006, 2007. Then you can recover the 3D structure in front of the car and the motion of objects, here color-coded. Red means moving, blue means stationary in world coordinates. And this kind of 3D understanding and also motion inference is vital for predictions, because the motion information allows you to predict into the future. You can say if that same obstacle keeps going at the same velocity, then it will be in the driving corridor in the next few seconds. And clearly, the further we can predict into the future, the better we can analyze the 3D structure in front of the car, the more we can save lives, avoid accidents, etc. And one of the ambitions that we have is to push computer vision and camera-based sensing to enable that 3D perception. And as you know, to date in the automotive world, 3D perception is largely done with LiDAR sensors, laser-based sensing, but I'm a strong and firm believer in cameras. Cost, for one thing, is a big difference. but I'll come back to that. Another area that we've worked in on autonomous systems is drones, quadrotors. This is a picture from my lab in 2007 back in Bonn. This was when, at that point, we built our own drones. You could not commercially buy them, but then at some point commercial drones appeared. This is a company, Parrot, a French company. This is Ascending Technologies, a company, that's a startup of TU Munich that was recently acquired by Intel. And then there's a lot of even very small drones like these nanocopters that fit in the palm of your hand. And one of the key questions that we asked is, can we use onboard sensors, in particular cameras, to sense the 3D world in real time and enable autonomous navigation? And obviously, this can be done. Here's some examples. This is from back in 2012. We used the cameras on the Parrot drone, and as you can see, this is the onboard view. We can track points, we can recover the 3D trajectory, and thereby fly off some, for example, predefined trajectories. As you can see here, it follows the predefined trajectory fairly accurately. And then you can do all sorts of other things. You can, for example, train the system, or not train, but basically make the system hover in one specific location in space, and then use the onboard sensors to always kind of recover that desired location. This was the lead developer, Jacob Engel. This was his master thesis. And you can see it sometimes it loses tracking. Once it doesn't see the familiar world, it recovers the track. And he shows that you can really push it away in all sorts of nasty ways. And much like a little dog, it always comes back. You can even cover, the front sensor, the camera. You can cover the ultrasound depth sensor, and still it finds its way back to where it should go. This is a demo that we often like to show on public events, partially because these drones are fairly human safe. Here you see it actually collides into the wall, but it doesn't matter. This is much better for the nano drones, the little ones, because once they fly into the wall, they don't typically damage themselves or the wall. The bigger ones, you never know. Some of the big ones we had, they're a little bit like dogs, fairly aggressive also. They can bite, sort of. So the nanocopters are nice. If they fly into your head, for example, you hardly notice. So this is very important for autonomous systems in the human environment. There should be ways to... Oh, sorry. So what we saw there was a nanocopter that we equipped with a camera. And then we can also do autonomous flight. This was 2014, autonomous flight with a nanocopter. I think I'll move ahead here. But basically very similar things that I showed before. What I want to talk about today is 3D understanding of the world, how you can use cameras to recover the 3D world and the location of the camera, and how that can be used for autonomous machines, autonomous systems. First of all, 3D reconstruction, a very classical problem, and there's many leading experts in the field sitting here, people like Ronnie Kimmel and others who have pioneered all sorts of computer vision techniques that we can use to recover 3D worlds. There's actually surprisingly many ways that people devise to recover 3D from cameras. For example, you can use shading information, you can use even blurring information to recover, you can use symmetry, all sorts of criteria. But one of the most powerful techniques to date is this concept of color consistency across multiple views. Leading to this approach called multiple view reconstruction. And here's kind of the key reasoning. If you have two images, and let's say you know where they're located, you know which way the cameras are facing, if in addition you knew the correspondence between points in either image, then you could infer by triangulation the 3D location of that point. In practice, you don't have that correspondence, but what you can do is you can tackle the problem from the opposite vantage point, go into 3D and say, how likely is this point on the surface of the object? If it is on the surface, then once I project into pairs of images, I should be seeing the same color here. Whereas if I look at points, say, out in 3D space or inside the object, once I project into the cameras, I don't tend to see the same structure because I'm not looking at the same thing. And so by checking in the projection of all 3D points into pairs of images and checking for color consistency, I can somehow distinguish points that are likely on the surface from points that are likely not on the surface. And I can do so by basically associating with each point in that virtual 3D space a value of what's called photoconsistency, and by convention I would take an interval 0 to 1 and assign low values near 0 to points like the green one and high values near 1 to points like the red one. Once I have done that for all points in that virtual volume, I can phrase reconstruction as a surface minimization problem where I say find a surface S such that the photoconsistency rho integrated across the surface should be as small as possible. The problem with these cost functions is that they are not convex. And then if you do optimization in the space of all conceivable surfaces, that is an infinite dimensional space. And so, you know, the classical approach to these problems was to say, let's initialize appropriately and then do gradient descent. I'm sure many of you are familiar with this concept. It's, for example, the same concept people use today to train neural networks. And if your problem is not convex, you never know exactly what you're getting. And that is indeed what happens in the neural network community these days. And so it's a question of having appropriate initialization strategies, etc., etc. For some of these problems, it actually boils down to having an oracle that actually knows what the right solution is. And then you initialize with the right solution or something close to it. And then... But it basically means that these strategies are not well suited to scale to the big data age, where, for example, if you do medical segmentation of organs, you cannot have a doctor initialize appropriately on each of millions of, you know, scans that they do nowadays. So we need kind of more elegant solutions that avoid this issue of appropriate initialization. In fact, this is usually where my students come back to me. When I tell them to re-implement some algorithm, you know, once it comes to experiments, they come back and say in the paper it says we initialize appropriately. What does that mean? Yeah, we all know what it means. It means it's not black box applicable. So what we came up with, though, was a breakthrough in this context of 3D reconstruction. We showed that these types of energies can actually be minimized globally by convex relaxation techniques. I don't want to go too much into technicalities here, but the idea is that you can compute a global minimizer by rephrasing this problem by an equivalent convex one. Equivalent means there is an efficient way to map the global minimizer of the convex problem to the global minimizer of this original problem. And as a result, we can take a set of images, compute these photoconsistencies. Typically, we take about 20 or 30 images, and then we can initialize not appropriately, but randomly, say like with a box, and then the algorithm will carve out the provably optimal reconstruction efficiently. When I say efficiently, this is common knowledge. It doesn't necessarily mean fast, right? This took an hour to compute on the latest GPUs in 2008, 2007. We managed to improve things. This took 3 minutes for each time step. So as you can see, we can use camera-based techniques to recover not only one surface reconstruction, but entire actions in space and time. And this is where you can go well beyond what you can do with LiDAR or laser-based sensing of the world. The LiDAR scans point by point, line by line. With cameras, you get much richer information with a single time step. In addition, you can not only recover 3D over time with camera-based techniques in a way that you cannot do it with laser, but in addition, you can, cameras are much cheaper. Cameras are much more lightweight, I started with the story of the Daimler manager who said the $3 camera was too expensive. I'm not sure what he says about all the LiDARs they put on cars nowadays. These LiDARs cost thousands of euros. People have been announcing low-cost LiDARs. I would call them lower-cost LiDARs because they're still a factor 100 away from what the price of a camera. And cameras are omnipresent, and you will see with some of the algorithms we've developed, we can reach levels of 3D perception that are camera-based that can essentially rival with some of the capacities of LiDAR. The previous approach, we assumed the cameras were put in a known location, were pre-calibrated. Obviously, in, say, an autonomous systems, you typically don't know where your drone is, where your car is, and hence where your camera is. You have sensors like GPS that tell you roughly the location, but not very accurately, and often GPS is not available in cities, in tunnels, in parking garages. There's a lot of multipath problems with GPS for localization, so you need to devise methods, camera-based techniques to reconstruct and localize. And this is a problem that was traditionally called structure and motion, or structure from motion, and recently has been called SLAM, simultaneous localization and mapping. And it's a very old problem. To give you one example, this is one of the pioneers in this field, an Austrian mathematician by the name of Erwin Kruppe. And back in 1913, he proved that if you see two images of 5 points, corresponding points, then you can recover the motion between these two frames and the 3D location of these points. This was quite a breakthrough, and there was a number of such results more than 100 years ago. And for me, to date, this is one of the most puzzling things about history of science, how someone can study a problem like that, camera-based reconstruction, well before the advent of computers. At the time, first when I saw that, I thought, why would anyone study this problem if you don't have a machine to do the reconstruction? Well, at the time they did things manually. They labeled points in aerial images, for example. Here's the church tower in this image, here's the corresponding church tower in the next image. And once you have 5 points, you can do the reconstruction of these points and the motion of the airplane. So that's nice. And one should say then starting in, 60s, 70s, 80s, people started to develop computerized techniques to basically follow in the footsteps of Kruppe. So they said, let's take two images. And so here's some of the real-time capable approaches to this problem called visual SLAM. One of the first ones I'm familiar with that ran in real time was a method that was demoed around 2000, so at this point almost 20 years ago, in the lab of Stefano Soato at UCLA. And then there's been a lot of pioneering works, people like David Nister, E. Drummond, Klein and Murray. This is a very popular one, PTAM, because the code is online, you can use it. This is another extremely popular one more recently, ORB SLAM, from a team in Zaragoza, quite a powerful SLAM approach. Most of these approaches, including PTAM and ORB SLAM, are so-called key point-based techniques, and they follow very closely in the footsteps of Kruppe. They take two images, they extract points, they compute correspondence between points, because Kruppe said we need corresponding points. And once you have corresponding points, once you've extracted points, once you've associated them in terms of corresponding pairs between the two images, then you can recover camera motion and 3D structure by approaches like bundle adjustment, for example. This is the classical way to do it, and you can see it was inspired by some of our heroes, people like Kruppe. But I think one of the important messages that I always give to all of my students is, no matter how pioneering a researcher was, you should always question whether this was the right solution. And this is something important, and I think it's something that drives all of us as researchers to question everything that's been done before. And I would argue that Kruppe was pioneering, but he may have been also quite misleading. Why? Because when I switch on a camera today, first of all, I don't get two images, I get a whole stream of images, 30 images. And the decision to select two consecutive ones is somewhat random and partially due to the fact that in the 80s you couldn't process more than one or two images in anywhere near real time, but that has changed today. Secondly, the camera doesn't actually give me points, and most certainly not corresponding points. It gives me colors, brightness, values, intensities, etc. And so the assumption that I have points and the assumption that I have corresponding points is a very bad assumption. First of all, if you select some points here using, some corner detector or whatever, why do you take these points? Why do you throw out all the remaining information that your sensor provides? Basically, at step 1, you throw away 99% of your sensory data. That cannot be an optimal solution. Anyone who does sensor analysis from, say, a statistical perspective knows the closer you stay to the original sensor data, the more optimality you can get, and that affects precision and robustness. Secondly, this correspondence estimation, let's face it, it's one of the nastiest problems in computer vision to solve it. And, people devised sophisticated techniques like SIFT, SURF, brief descriptors that try to tell you this point is this point and here is the same point. And then, there's all sorts of strategies like random sampling consensus to filter out the bad correspondences. Because once you make a mistake in that intermediate step, it's going to deteriorate all your results subsequently. You cannot, so any bad correspondences you cannot really recover from in this step. So what we promoted among other people over the last years are so-called direct methods to tackle this problem, where you aim at directly recovering from the sensory data, the brightness values of your camera stream. You try to recover camera motion and 3D structure. People often ask, what is really the difference? Because in the end, you will see we also compute 3D points. The key difference is not that they do points and we don't do points. No, the key difference is the cost function that's being minimized. Here, in the key point-based classical techniques, people minimize a geometric reprojection error. You project points into images and you aim at minimizing the discrepancy geometrically. What do we minimize? We minimize a photometric error, color consistency. So basically the key idea behind direct methods is you say find a reconstruction of the world and a motion of the camera such that when I project these colors into this world and back out into the other sensor, the colors should match, should coincide. And so what drives everything is the color consistency. Whereas here, you use color consistency to associate points, and you kind of separate the two problems, and once you have corresponding points, you do 3D reconstruction. So here, direct means you do everything in one, derived directly from kind of a brightness consistency constraint, very much like in optical flow. One of our first approaches in this line was a technique that I called LSD slam, large-scale direct slam. The name was, I think, quite useful for promoting this work. I should say most of this work was done by Jacob Engel. I would say my most important contribution was to bring up the name LSD slam. Jacob said, Daniel, that's the name of a drug. I said, yes, that's exactly why we're going to use it. It paid off. This is by now my most cited paper ever. Most certainly only because of the name. It's a somewhat involved approach, and this is kind of a rough overview. It starts with a video coming in at, say, 30 hertz, and then there is one thread that does tracking of the camera and one thread that does depth estimation, and then we alternate, and then there is a pose graph optimization that makes it large scale compatible. I don't want to go too much into detail, but I want to highlight in what sense this is a direct approach, or what we mean by direct here. The tracking is done in the following way. So we have a keyframe, we store keyframes over time, and then we have the current frame, the brightness at the current frame at a pixel location X, and then we say try to align the current frame to the keyframe using some rigid body transformation, G, Xi, Xi, then 3 degrees translation, rotation. So find the rigid body alignment that warps the current frame onto the keyframe. Very much like in optical flow, except it's only 6 degrees of freedom. And so that can be minimized in a coarse to fine manner that we adopted from our previous optical flow works. And so you can do this even on a single core of a CPU easily in real time. And then on the other core, you can run the mapping, the depth mapping, and that way you get something that runs in real time on a simple laptop CPU. And as you can see here, this is the camera. It runs on this laptop CPU. It estimates the motion of the camera, and it estimates a semi-dense reconstruction of the world. And here you see some examples. On the top left is always the input images, and in real time on this laptop CPU, we can recover fairly large environments at fairly good level of accuracy. The large-scale precision comes in through this pose graph optimization that makes everything globally consistent. Here's demos that we did after the presentation at ECCV. Here you see a little bit what we mean by semi-dense is roughly 50% of pixels are associated at depth value. So another difference, the key point-based reconstructions, typically you can't really see what's in them unless you've worked in this field forever. Then you can read point clouds, but I find these reconstructions, I could see the things in the world myself, so they are much denser and much richer. One of the issues, though, of LSD SLAM was that we had this alternation between mapping and localization, right? One thread that estimates camera motion, one thread that estimates 3D structure. And as Krupa already showed, this is a coupled problem. It's a chicken and egg problem. So decoupling it into two alternations doesn't seem like the optimal approach. And so I pushed Jacob to look more into it to see, can we not do things jointly in what you could call a photometric bundle adjustment. And one of the key challenges to make this work in real time is if you take a lot of points and a lot of camera poses, then the Gauss-Newton optimization that you typically do to jointly estimate pose and camera poses and inverse depth values, this gets to be very computationally intense. In the Gauss-Newton step, you have to invert a Hessian matrix. And typically, this Hessian matrix has this block structure where you have a fairly small block that involves the camera poses. We constrain this to a sliding window, typically 7 or 8 keyframes to make it work in real time. And then we have the depth values. These are typically like 100 million parameters that are in there. So that's quite a lot of numbers. So this block is extremely large. And unfortunately, in LSD SLAM, because we used some spatial smoothing, it was not diagonal. So there was a lot of off diagonals and very hard to invert. Instead, in this approach that we call direct sparse odometry, we take a sparser set of points, more sampled, more kind of equidistantly, and we don't do spatial smoothing. As a result, this matrix gets more diagonal, and that enabled us to actually do the inversion in real time using a trick called the Schur complement trick. Don't want to go too much into the numerics here, but somehow this allows us to jointly optimize pose of camera frames, at least in a sliding window, and depth values, and that created a significant boost in precision. Here's results of this technique called direct sparse odometry. It's the follow-up to LSD SLAM. Here you see the input video, just a single handheld camera. We walk through a subway station. There's actually people walking through the scene. The algorithm assumes a static world, but moving objects are kind of just filtered out automatically. As you can see, there's often very limited texture, just gray streets, not a lot of points, just, sky, cloudy sky. But still, it can cling on to all the structures it sees and recover the 3D, the trajectory of the camera, that single camera, at a very high level of precision. Obviously, once you track a camera frame by frame over thousands of frames, you accumulate errors in the estimation of the camera motion, and these aggregate into what's called a drift. You see the drift here, that bicycle in the image is recovered twice here, right? So there is an offset, a drift of maybe 2 or 3 meters on a distance of hundreds of meters. So you can say the precision, if you will, if you want to measure it in this way, its translational precision is in the range of less than 1%. The question, though, is how can we quantify that? And this is one of the biggest challenges in computer vision in general. On one hand, we want to, we want to be able to quantify our algorithms. On the other hand, we want them to work in the real world. And commonly people simulate data and then they have ground truth where the camera was and then they can quantify, but then you know the precision in the simulated world. And this is one of the biggest problems for autonomous driving is, can we transfer the performance from the simulated world to the real world? Let's put it this way. If I were to sit, if someone were to give me a self-driving car that works perfectly in the simulated environment, I would not drive around in it. And so what did we do here? You can set up a mocap system to get ground truth in the real world in a room like this, sure, but then you only know the performance in a room like this. I cannot deploy a mocap system in the entire subway station and out on the other side. That just doesn't scale. So what did we do? We just recorded lots and lots of data, like the subway example I showed you. Very diverse with different lenses, indoor, outdoor, different, faster, slower motions, more rotational motions, all sorts of different motions and environments. All the environments where we wanted our technique to work. These sequences are very diverse, but they all have one thing in common. They all loop back to where we started from. And hence, so then, much like in the bicycle example, I can align the last frame of the sequence to the first one, and then I know where the last frame was. So it means for each sequence, I don't know where the camera was halfway through the sequence, but I do know where it should be at the very end. And then I can compute this overall drift for every sequence, and if we have enough sequences, that gives you a reliable estimate. And so this is what we show here. This is quantitative evaluation compared to what we consider the state-of-the-art in real-time visual SLAM. This technique, I mentioned it, called Orb SLAM from Zaragoza. Quite a powerful and popular technique. Here's the plots. This is the translational error. This is rotational error. This is the scale drift. And here's the number of sequences where we achieved a certain error. And obviously, you want to be in the top left corner. You want to have as many sequences with as low an error as possible. You can read these plots in many ways. The real-time capable method is the dashed one. And if you have a little bit more compute time, you can get a little bit better precision, as you can see here. You can read them in many ways. For example, you can say, what is the maximum error on the best 300 sequences? Orb SLAM has an error of around 6. We have an error of around 1, which means the error is reduced by a factor of 6. That's almost an order of magnitude less error. Right, this is important because we live in an age where once you have a deep net to do object classification and you get 0.5% better than the state of the art, you can publish a paper. In fact, even if you're 0.5% worse, you can publish a paper. This is not 0.5% improvement. This is an order of magnitude almost that we're talking about here. So it was a completely different ballpark. Similarly, you can say in terms of robustness, let's say I want to fix the error to 2. How many sequences out of 500 can I track with that error? Orb SLAM can track 100 out of these 500. We can track 400 out of 500. So it also means a significant boost in robustness. Because, of course, for every method you will find some sequence where it works well, but you want to make sure it works in all diverse realms. Anyway, you see the performance was quite good, and tracking cameras in real time at high precision and robustness is obviously something important for the commercial world. And so we decided to create a startup company called Artisense. Last year we raised over 4 million in seed funding, and we built up a team, a fairly sizable team of researchers and engineers. Predominantly we have offices in 3 locations, Palo Alto, Munich, and Tokyo. This is a picture of a recent team event. What are we developing? Well, we are, this is some of the works that were done by Artisense researchers. Here we actually deployed SLAM on a drone to show you can localize the drone with our SLAM algorithms. And in contrast to the previous example, you can not only do autonomous navigation of some, say, predefined trajectory, as shown here. But you can do more. You can, for example, do a full 360-degree loop. We'll see that in a second, where the drone turns around 360 degrees and you get an entire map of the whole room. Because the SLAM algorithms are large-scale capable, so we can, in real time, map our environment at large scale. And thereby you can use drones, and we've done that in follow-up works where we use the drone, here's an example, to not only map the environment in real time, but then to do things like obstacle avoidance, path planning, trajectory optimization, etc. So we can compute volume occupancy maps, we can compute shortest paths, and thereby do things like obstacle avoidance. For time reasons, I think I'll move on, but what happens in this demo, or maybe we can leave it here, you see the onboard camera view. The algorithm the drone is programmed to move around to maximize the free space, and then it can compute traversable regions and compute shortest paths, as you see here in 3D. And then in the end, it autonomously flies through the doorway without anyone telling it to do so. So this is also, first efforts into autonomous exploration using vision-based SLAM on drones. At Artisense, we're also developing hardware systems, not because we see ourselves as a hardware company, but because current hardware doesn't often, suffice in terms of the ingredients, the methods. So here we have a system that involves stereo camera rig, GPS, GNSS, and inertial sensor all fused properly. And we develop cloud-based processing of this data. We have a large car that we use for demos, but we also develop small cars. Here's a toy car we developed earlier this year that has essentially the same sensor system inbuilt, and so we can demo, and it has onboard processing on an embedded system. What do we do? Here's an extension that we developed at Artisense, an extension of the DSO to stereo. And as you can see, now we can do really large scale, and one of the benefits of the second camera is that we actually can get the scale of the world. And so we can drive around, as you can see here, we drive around a block and the drift is essentially zero. Things actually line up quite well, and so you have a technique which in real time allows you to map the entire 3D world and track your camera or your car at very high precision using only 2 cameras. Nothing else, no GPS, no inertial. We are also fusing with inertial. We have shown there's a visual inertial DSO where we can also get scale through the inertial sensor and get additional precision and robustness. But here this is just a 2-camera version. There's many ways you can improve and boost the precision, and this is one of the things we've been focusing on at Artisense. One is by introducing additional sensors, additional cameras, inertial sensors, GPS. All of this is fused optimally into the estimates. But another key challenge these days is how can we make use of deep learning for SLAM? And most of you, I'm sure, are working in this field of deep learning today. As we all know, deep learning has swept most areas in computer vision, but there is one area where classical methods prevail as the best performing, and that is 3D reconstruction and SLAM. And, it would take a long time to discuss why deep learning so far has not been very successful. There have been many efforts starting around 2016-17. Here's some example works in this field where people use deep networks for visual SLAM. But the key problem with all of these approaches is they don't provide state-of-the-art performance, meaning in the end the classical SLAM algorithms outperform them still. They cannot compete. The deep learning-based methods cannot compete. And the main reason, in my view, is that often people tackle this as an end-to-end learning challenge. In go the camera data, out comes a 3D world and trajectory. What we promoted last year at ECCV is you can actually, turns out, use deep networks to predict depths from just one image. So you get an image, you predict the depths. We drastically improved the network to predict depths, so you can see we can predict the depths at much higher precision from just one single image using training data. And then we can use that depth prediction and feed it into a SLAM algorithm, both as initialization for the SLAM algorithm, but also we can say find a reconstruction of the world such that it's consistent with what the network predicted for each keyframe. So we can kind of have a cost function that couples it to the deep net prediction. What does that give us? Well, one of the aspects of this prediction is it gives us the scale of the world. And so we get scaled reconstructions from just one single moving camera. And what you see here is, to my knowledge, still the state-of-the-art in real-time capable monocular SLAM, single camera on the Kitty sequence here. And we get essentially the same precision as with the stereo method, except we only use one camera. So loosely speaking, the second camera is hallucinated by the deep network. That's why we call it deep virtual stereo odometry. It's not actually stereo, we just hallucinate the effect of the second camera. And you can compare, here's the ground truth, this is the monocular DSO, stereo DSO, and this is the mono version enhanced by a neural network. Here, other examples, we see that here's a quantitative evaluation. These are some of the top stereo methods. Stereo LSD SLAM, stereo ORB SLAM, stereo DSO. These are the sequences we trained on. These are the sequences we did not train on. The solid numbers are the best performing method in each row. And here is the monocular method that uses a deep network. And as you can see, even on the sequences that we did not train on, we often outperform the best stereo method with just a single camera. And so this is the breakthrough. So we get very precise maps of the world in 3D, all computed in real time. Here you see some examples. You can see the precision by the sharpness of the structures here, even the lines on the roads, etc. We can use deep networks also to enhance that 3D perception, compute semantic point clouds. Here, red is the drivable area, yellow is the sidewalk, blue is cars. We can detect all sorts of objects, whatever is desired and necessary for the application. This was a project in Berlin where we deployed our sensors on a fleet of cars and showed that you can simultaneously map and merge the world in real time and merge these maps in the cloud and get very large-scale reconstructions. These are just a few screenshots from the Berlin project. So we mapped like there was, I think in total was 8,000 kilometers of driving that we did in the Berlin project with a fleet of cars and created large maps of this type. Here's more examples from the Berlin project. So these are very large maps of towns, all created in real time. Okay, I'm running out of time. I talked about driver assistance, self-driving cars, our beginnings back in 2005. I talked about more recent developments in real-time visual SLAM, the so-called direct methods that significantly increase precision and robustness. I showed you can further enhance precision and robustness with deep neural networks to really get state-of-the-art SLAM performance by, say, a hybrid between deep networks and classical SLAM approaches. I showed you can deploy them for autonomous systems, for cars, for drones, etc. And you get 3D maps, you get localization, and semantic scene understanding, 3D scene understanding, all computed in real time. Thank you very much.